Okay, we have seen the molecular orbital approach to hydrogen molecule, and now we will look at the valence bond approach. We saw that the molecular orbital approach does not describe the dissociation limit correctly, and in valence bond theory the dissociation limit is actually described correctly, because it starts from the dissociation limit. So, let us imagine that I start with the molecule at such that the distance between the two atoms is very large. So, let me say here is my molecule, the distance between the two atoms is very large, and if the distance is very large, what would I expect? I would expect that there are two separate hydrogen atoms. So, if this is nucleus A and if that is nucleus B, what you will have is one electron sitting in this atomic orbital 1s A, and you will have the other electron sitting in this other atomic orbital, which we label 1s B. And the two systems are far apart. Let us say if the two systems are far apart, they are not really interacting with one another, they are independent of one another, and if they are independent of one another, the total wave function for the system will be the product of the wave function for the individual systems. So, therefore, you would have the total wave function given by 1s A. Let me say electron 1 is in 1s A and electron 2 is in 1s B. So, therefore, if the two are not interacting, the wave function, total wave function will be the product, and you can imagine that I will use this as the trial function. Well, maybe I will use the symbol 1 and 2, that will make the notations easier to write. So, now I can say, well, let me take this function, actually it is a very approximate wave function, but what I will do is I will use this as my trial function, which actually means that even at finite distance, even when they are very close to each other, I will say, okay, the wave function is simply a product of this form. Electron 1 is associated with nucleus A, electron 2 is associated with nucleus B, and they are sitting in separate atomic orbitals. There are interactions, I know that, but I can try and find out how good this is as an approximate function. So, people have done this, and if you did the calculation, what happens is you will get a potential energy curve. What do I mean by a potential energy curve? A curve in which the electronic energy is plotted as a function of internuclear distance. We have been doing that, though I did not use the word earlier. So, I will get a potential energy curve for the system, which would look something like this. Okay. In this case, if you did use this as an approximate function and did the calculation, you will get a potential energy curve of this form, whereas the actual potential energy curve we have seen, it decreases, it has a dissociation energy of 4.72 electron volts. While if you use this as the approximate function, you will get something like 0.4 or even less, right. The binding energy or the dissociation energy is extremely small, and it says that the system is only slightly stable, in contradiction with the experiment where the system is found to be quite stable. So, therefore, it is obvious that this is not a good approximate wave function. But then you look at it physically, I mean physically this function is not a great function, because you are saying that, okay, electron 1 is always associated with nucleus A, electron 2 is always associated with nucleus B, but even when the nuclei are very close, you are saying, okay, electron 1 is restricted to be confined to 1s A and electron 2 is restricted to be confined to 1s B. But when the distances are very close, we cannot say which electron is where. So, therefore, when the distances are small, definitely the electron 2 may be associated with nucleus A and 1 may be associated with nucleus B, and therefore, there is another possible function, the other possible function being 1 as A2. Notice what is happening, I am interchanging the 2 electrons. At close distances, definitely the 2 electrons can change places. So, I would have 1 as A2, 1 as B1 as another possible function, correct. Now, if you want, you can use this alone as your trial function, and then you will find that that again leads to exactly the same result, and therefore, that alone itself is not a decent approximation. But if that is the way it is, what will you do? You will say, okay, I will take the first function, I will have a function of the form which is contains the first function, and I will also have the second function. Right. I take both the functions and multiply the first one by some coefficient C1, the second by some coefficient C2, and add the 2 up. Right. Notice what is happening here. I am saying electron 1 is associated with nucleus, electron 1 is associated with nucleus A, electron 2 is associated with nucleus B, but then at close distance I allow the electrons to exchange places, and I get this function, and that should also be important. And now, if you have such a trial function, what will you do? You have to determine C1 and C2 in a variational fashion, but it is not really necessary to do the calculation, because physically we can guess what is going to happen, because you see these two are actually kind of equivalent, and therefore, they should make the same amount of contribution to the final wave function, right, because all that you are doing is interchanging the 2 electrons. Right. So, therefore, this and that should have the same amount of importance in your final wave function, and that this immediately tells you that you have 2 possibilities, just as in the case of molecular orbitals that were discussed earlier in the case of S2 plus. You will have a possibility of C1 being equal to C2, and the other possibility will be the negative sign, C1 being equal to minus C2, right. So, therefore, we have now 2 functions. What are these 2 functions? Let me write them. My first function will be phi, which I will denote as 1 as which I will write as 1 as A1, 1 as B2. With the positive sign, I will add the other one, 1 as A2, 1 as B1. This is just similar to what happened in the case of S2 plus. S2 plus I had 2 atomic orbitals, they added together with a positive sign, or they added together with a negative, one of them having a negative sign. In a similar fashion, I take the first function, but these are not molecular orbitals, remember that, because these are actually wave functions for 2 electrons, not 1 electron. This is a wave function for 2 electrons, this is a wave function for 2 electrons, and I am adding these 2 functions. So, I add the 2 up. Naturally, what will happen? I will have to have a normalizing factor here. It is possible to determine the normalizing factor. I will not write it down, I will not calculate it, but it is easy to show that it is given by 1 by square root of 2 into 1 plus s square. In the case of molecular orbital theory, there was only an s. That is because you are adding atomic orbitals, but here you are adding 2 electron wave functions, and that is why it is s square. And this is one possibility. What is the other possibility? The other possibility is to have 1 as A1, 1 as B2, minus 1 as A2, 1 as B1. And naturally, the normalization factor will be different. All that will happen is you will have 1 by square root of 2 into 1 minus s square. S is actually our overlap integral that we had earlier. Okay, so, there are these 2 functions. The first one I am going to call it valence bond approximation for the, actually this will turn out to be the approximation for the ground state, and this will be a valence bond approximation not for the ground state, but for an excited state, as similar to what happened in the case of molecular orbital theory. This will represent the ground state, this will represent a possible excited state of the system. Okay. So, now you can do a calculation using this function. You use this as the trial function. For each distance you will calculate the value of script t and then make a plot of that script t against the distance. So, actually what happens is you will get a curve which looks like this. In comparison with this, the simple molecular orbital theory curve, this is valence bond theory. This approximate function is known as the valence bond wave function for hydrogen molecule, and in comparison with that the molecular orbital results are something like that. So, these things are there in the picture that I showed you earlier. We will have a look at it once more. So, this is the experimental, this one is the experimental curve, that is the valence bond result, and this curve is the molecular orbital result. You can see that valence bond theory actually is better in two respects, better in that it describes the dissociation limit correctly, which is not surprising because that is how we started with the wave function, that is how we constructed the wave function. So, that part is not surprising, but you also find that the energy predicted by the valence bond theory actually is better than the molecular orbital theory. Let me tell you the value of dissociation energy as well as the bond length. I will list the values of Re and the dissociation energy. Simple MO theory which we have discussed earlier, it gives you Re to be 0.83 angstroms and dissociation energy to be 2.65 electron volts. Valence bond theory gives you 0.80 and 3.16. In comparison with this, the experimental values 0.74 and 4.72. But even though valence bond theory is better, you see it is that is true, correct, thank you, it is electron volts. So, even though the valence bond theoretical answer is better, it is still far away from the experimental value. It does predict that a bond is formed, and it predicts the bond length to be, I mean, not a bad value, 0.80, whereas the experimental value is 0.74. So, therefore, you can see that there is still room for improvement, correct. So, people have done so many kinds of calculations, many calculations have been done. All these calculations were done long ago. For example, what you can do is, I mean, I can tell you one typical way in which the modifications will proceed. These atomic orbitals, right, 1s A and 1s B, they are taken to be atomic orbitals, each one of them is taken to be atomic orbitals which feel the nuclear charge of unity, right. They are taken to be the same atomic orbitals as in the case of hydrogen atom, and in the case of the hydrogen atom, each electron, not each electron feels only one nuclear charge. But here you have two nuclei, and therefore, maybe what would happen is that the effective nuclear charge felt by these atomic orbitals need not be unity, but it may be a new number different from unity. So, you can introduce an effective nuclear charge, but once you introduce an effective nuclear charge, you will have to do a calculation for different effective nuclear charges and find out which effective nuclear charge is the best. and this will lead to an improvement in the energy of the system, and people have done this kind of calculation. Okay. I will tell you details of one such calculation, not details, but I will give you essentially the answer for that. But before I do that, we have to understand why is it that the molecular orbital method gives a totally wrong dissociation limit. We will try to understand that. So, we look at the molecular orbital wave function. Oh, before I go into that description, I should also tell you what happens if you did a variational calculation using this as the trial function. In that case, you will find that there is no bond formation, but the system is actually repulsive meaning there is no formation of a molecule, there is no bond formed. If you say that, that is the wave function for the system. Okay. And so, it is some excited state of the system. So, let us forget this, we are not interested. This is the case where there is a bond formed. And now, we will look at phi MO once again. What is phi MO? It is actually sigma g 1s with the first electron and sigma g 1s with the second electron, right. And what is sigma g 1s? Let me just remind you, it is given by 1 by square root of 2 into 1 plus s into 1 as a 1 as plus 1 as B1, that is sigma g 1s, and sigma g 2s has a similar appearance. It will also contain this factor 1 by square root of 2 into 1 plus s. So, effectively there are two such factors. So, I will have the square of that, and then I would have 1 as A2 plus 1 as B2, correct. Now, this is just a normalization factor. Let us worry about what is in the wave function. So, it is actually going to be, if I squared this, I will get 1 by 2 into 1 plus s multiplied by, you see there are two terms here, there are two terms there. So, if you multiplied out and added them together, you will get 4 terms. I am going to write those 4 terms. The way I am going to write those 4 terms is like this. I am going to multiply this with that, that is actually 1 as A1, 1 as A2, right, and then I will multiply this with that. So, this plus 1 as B1, 1 as B2, and then I will have what are referred to as cross terms. So, this multiplying that is actually 1 as A1, 1 as B2 plus 1 as A2, 1 as B1. So, this is exactly what my molecular orbital wave function is for the hydrogen molecule. Is it okay, or have I made a mistake? I do not think I have made a mistake, right. But then if you look at this function, you will notice something very, very interesting. See, if you looked at this part of the function and compared it with the valence bond wave function, you will find that this and that are the same. So, contained inside your molecular orbital wave function is actually the valence bond wave function. And what does the valence bond wave function say? The valence bond wave function says that there is one electron associated with nucleus A, right, and if that is the way it is, the other electron is associated with nucleus B. And if you look at this one, what will happen? The electrons simply have interchanged their positions. So, therefore, what is actually happening is that there is one electron with the nucleus A, one electron with nucleus B, right. And further, I think this is the best point for me to introduce the spin part of the wave function. Let me just introduce the spin part for this function. How would the spin part look like? Well, here I have written only the spatial part of my wave function. And if you looked at the spatial part, if suppose you interchange the electrons 1 and 2. Suppose you interchange the electrons 1 and 2, what will happen? This function, if you interchange the electrons 1 and 2, you will find that this function does not change sign. And therefore, strictly speaking, you see the wave function as it starts does not satisfy the Pauli's exclusion principle, but then you can make it satisfy the Pauli's exclusion principle by adjusting the spin part. So, how would the spin part look like? It would be 1 by square root of 2 into alpha 1 beta 2 minus beta 1 alpha 2. Remember, we have seen this kind of spin function earlier, and this function has the nice feature that if you interchange the two electrons, the function will change sign. So, therefore, along with the spin part, if you took this function, what is the result? The result is that it is antisymmetric. Similarly, for this function also you can use exactly the same spin part. For the molecular orbital function also you can use exactly the same spin part without any difficulty, because when you interchange the two electrons, you see this function does not change sign, and if I use exactly the same spin part, everything is fine, the wave function satisfies the antisymmetry principle. Now, if you look at this function, it says that one electron is associated with the nucleus A, the other is associated with nucleus B, and further it says that okay, one of them, if it is pointing up, the other is pointing down. Now, this is actually very nice for the chemist, because you see, if you remember what Lewis said, or what chemists were thinking of the formation of a bond in hydrogen molecule. They would say that you have one electron from hydrogen 1 and hydrogen A, and you have the other electron from the other hydrogen, and these two electrons are paired. And a bond means a pair of electrons which are actually paired in such a fashion that their spins are antiparallel. Right? That is the Lewis way of thinking about the bond. The electrons form a pair, and so you have a bond, and you will see that the valence bond description actually is very much resembling that, because you are saying okay, the two electrons are paired, their spins are antiparallel, and when one electron is associated with the nucleus A, the other electron is associated with nucleus B, and these two electrons are getting paired. Okay. And you will also realize that the same thing is contained inside the MO function. The same thing is contained, but the MO function has other possible contributions also from a case like 1 as A1, 1 as A2. So, how will I represent that? Well, you can say okay, this represents a situation where the electrons are shared equally by the two nuclei. This part represents the case where the electrons are shared equally by the nuclei, but if you look at this 1 as A1, 1 as A2, this means that both the electrons are associated with nucleus A, while that represents the situation where both the electrons are associated with the nucleus B, and therefore, if I wanted, I can say that this one represents a chemical structure which I will denote as H minus H plus, while this part represents a chemical structure. According to a chemist, it would represent a structure which would be written as H plus and H minus, right. This is actually H minus and H plus, this will be H plus and H minus. Yeah, okay, there is a plus there, right, because everything is being added up. Okay. So, therefore, if I looked at the molecular orbital description, what happens is that contained in the molecular orbital description are the valence bond wave function, which is this. It also has contributions from what may be referred to as ionic structures. These are the ionic structures, right. And if you looked at the contributions from ionic structures inside the molecular orbital wave function, you have the ionic structures, but what happens is that the ionic structures and this structure, which is actually referred to as a covalent structure, this one, because you see it is representing a covalent bond. So, this is covalent structure. So, the covalent structure and the ionic structures have the same amount of importance in this description. So, therefore, if you think of dissociating the molecule, what will happen? This is the system, the molecule may dissociate to give you 2 hydrogen atoms. That is what will happen if you had only this part of the function, but this part of the function implies that the system may also dissociate into the ionic structures which are H plus and H minus. So, if you dissociated the molecule, the molecular orbital theory will say that okay, it is possible for it to dissociate in such a fashion that you will get an H plus and an H minus, and that is the reason why the plot of energy, this is molecular orbital energy according to molecular orbital calculation. It does not give you the correct dissociation limit, it does not dissociate to 2 hydrogen atoms, but instead it dissociates sometimes. I mean, when you dissociate, you can get 2 hydrogen atoms because it contains this part, but you can also get a positive ion on one side and a negative ion on the other side. That is what molecular orbital theory says, and that definitely cannot be true. And this is the reason why MO theory gives you totally incorrect dissociation limits. Fine. But then you look at the valence bond theory. Valence bond theory actually has only the neutral structure. Now, if I wanted to improve the valence bond theory, what can I do? Well, these ionic structures are actually possible. That is the way in which valence bond theory would think. It would say that okay, these structures must be possible, but they should not have the same amount of importance as the covalent structure. So, therefore, an improved valence bond theory wave function can be written. How will I write the function? An improved valence bond theory function will have phi improved MO, improved valence bond would be, you will have this neutral structure, right. So, let me just say that it is written as some phi HH. I do not want to be writing all these things in detail, but when I write phi HH, maybe I will put 2 dots in between. What does that represent? It just represents this part of my function, right. And then I would have phi H plus H minus. What would that be? It would be this one. It would represent 1 as B1 into 1 as B2, and then I would have what this, the other one, phi H minus H plus. So, these are 3 possible functions, right, and what does the molecular orbital method say? It just simply adds all of them, right, with the same amount of importance and does the calculation, and that gives you wrong answers. Now, simple valence bond theory, what does it do? It does not include this or that, but it just says the function is just this. So, a better calculation will be to say that okay, I will take combinations of these things after multiplying them by suitable constants. So, what I will do is I will multiply this by maybe a constant which I will refer to as C1, and these 2 I would expect they hopefully would have the same amount of importance, right, because you see a structure in which you have H plus on one side and H minus on the other side, or a structure in which H minus is on this side and H plus is on the other side, they would make the same amount of contribution. So, therefore, these 2 I would expect would have the same amount of importance. So, what I will do is I will simply add them together, multiply them with a coefficient which maybe I should call this C1 and that C2. Now, if you did that, what will be your next step? You will take C1 and C2 to be variational parameters and find their values in such a fashion that script t has the least value. and because of the way the wave function is constructed, it is guaranteed that it will dissociate correctly, and it is also guaranteed that the energy will be better than the valence bond theoretical calculation, and such calculations have been done. There are too many curves in this picture, but anyway, let me draw this one also. If I can find chalk of a different color, I will use that. So, this one will actually lead to an improvement in the energy, and the bond length. So, this is improved valence bond theory. Okay. Now, I will write the answer of one such calculation. The bond length is actually 0.77 angstroms, and the dissociation is 4.00 electron volts. And I should also tell you that this particular calculation was due to a person called Weinbaum. And in addition to taking this as the function, what he did was he introduced this idea of effective nuclear charge, and varied the nuclear charge in such a fashion that he got the best energy, and you can see that the answer that he got for the energy was fairly decent. The dissociation energy was 4, and the bond length was found to be 0.77 angstroms. Okay. Now, you may ask, is it possible to improve molecular orbital theory, and the answer is that yes, it is possible to improve the molecular orbital theory also in a similar fashion. And in fact, if you try to improve the molecular orbital theory, what will happen is that you will get exactly the same kind of function. I mean, when you look at it in detail, you will find that the function is of this form, and such procedures are known as configuration interaction procedures. Now, even for a system like hydrogen molecule, these calculations, which are referred to as configuration interaction calculations, are very difficult. They are quite involved and quite difficult to perform. But I should also tell you that in the case of hydrogen molecule, there was a calculation done long ago by two scientists. Let me remove everything else. So, I will just say James and Coolidge, these were the names of the scientists who did the calculation. And effectively, I mean, they had large number of variational parameters, but you should also remember that the more variational parameters you have, the more difficult is the calculation, because each variational parameter you have to find its value in such a fashion that script T has the least value. And you see, those were days in which computers were not there at all. You had only not handheld, but you had only machines, I mean mechanical calculators, and using these mechanical calculators, they did a lot of work to get the best possible values for all the parameters, and then essentially you got the experimental